Colligative property is going to be the topic in this last lesson on a chapter on solutions. And a colligative property, simply put, is just a property of a solution that changes proportionally as you add solute. And one of the unique things is it largely doesn't matter what the identity of the solute is, but as you add more and more of any solute, these properties change. And these are things like freezing points. Freezing points go down as you add more solute, and boiling points. Boiling points go up as you add more solute. Things like the vapor pressure above that solution of that liquid are going to go down as you add more and more solute. So just some unique things. That's what we're going to study in this lesson. We'll look at some of the qualitative aspects of it, but we're definitely going to look at the quantitative aspects of it as well. Now, this lesson is part of my high school chemistry playlist. If you want to be notified every time I post a new lesson, subscribe to the channel and click the bell notification. All right, so colligative properties, and in this case, I just want to remind you of what's going on in a solution. In this case, let's just say we've got pure water. So not a solution, but just pure liquid water. And you've got intermolecular forces going on all throughout this lovely liquid. In the case of water, the strongest of those being hydrogen bonding. And so you've got this lovely network of hydrogen bonding. And what happens when you add a solute? And the big thing we need to look at is, like, let's say I just put something irregularly shaped right here, some solute. Well, all of a sudden, that's going to disrupt this network of hydrogen bonding going on with the water molecules. And that's why it turns out it doesn't really matter what the identity of the solute you add is. So because it's just not water. And as long as it's not a water molecule, it's going to disrupt the hydrogen bonding going on. And so it turns out, again, the identity of the solute doesn't matter, but how much of it you add, how many pieces you add totally does. And so because the number of particles you add is what really matters, well, then we have to take into account electrolytes, so that dissociate into multiple ions, multiple particles. So we have to factor that in, and we factor that in with what's called the Van Hoff factor. So represented by the symbol lowercase I, and it factors in when an electrolyte dissociates into multiple pieces. So if we take a look at, say, NaCl, and we'll look at barium hydroxide, one of your strong bases. We'll also take a look at methanol. And then finally, aluminum nitrate. All right, so turns out you've got to be able to recognize your electrolytes, and we talked about these way back towards the beginning of this course in chapter 3 or 4. In the case like NaCl, nice ionic compound that is soluble, one of your strong electrolytes, and it's going to dissociate into pieces here. In this case, you're going to get a single sodium ion and a single chloride ion, but a total of 2 ions per formula here. And so as a result, we would say that the Van Hoff factor is 2. So if it dissociates into ions, however many total ions it dissociates into, that's your Van Hoff factor. And the reason we got to factor that in, and let's say you've got a 1 molar solution of NaCl. Well, if it's 1 molar NaCl, that would mean 1 molar sodium ions and 1 molar chloride ions, but a 2 molar total concentration of particles, which again is what matters, the total concentration of particles. And so we're going to factor that in by taking that into account with this Van Hoff factor. So if we look at barium hydroxide in similar fashion, barium hydroxide dissociates completely to give barium 2+ and 2 hydroxides. So 1 cation, 2 anions, 3 ions total. And as a result, I equals 3. All right, so take a look at the other two. Let's take a look at aluminum nitrate first here. So aluminum nitrate's got a polyatomic ion. Technically, hydroxide was a polyatomic ion, but this one will ram the message home here. So the polyatomic ion itself doesn't dissociate any further, but you do get 3 of them. So you get 1 aluminum ion, 3 nitrate ions, 4 total ions, and your Van Hoff factor would be 4. So, and then finally, we've got methanol here, something you probably didn't know the name of, but methanol. And methanol is made of all nonmetals. It is a molecular compound. So, and the vast majority of molecular compounds are what we call non-electrolytes. So, turns out some of the ones that might act as an acid or base would be exceptions, like HCl, or things of that sort. But outside of those strong acids, most of the molecular compounds you're likely to encounter here are either going to be weak electrolytes or non-electrolytes, and I would just by default consider them non-electrolytes unless you for sure know better. And in this case then, it's not going to dissociate into any additional pieces. Every particle is just one particle. It doesn't give you any more particles. And so we say the Van Hoff factor is 1. Every formula unit gives you 1 particle. Cool, so for non-electrolytes, again, made of all non-metals, you should know the Van Hoff factor is 1. And then for your electrolytes, you should just be able to predict how many ions it dissociates into, and that's its new Van Hoff factor. All right, so I want to introduce our 4 fundamental colligative properties here. And the 4 different compounds we found the Van Hoff factors for a second ago. We're going to use those in a little bit, so I kind of copy them up over here so we can look back at them as needed. But our 4 colligative properties are going to be freezing point depression, boiling point elevation, vapor pressure depression, which is governed by what's called Raoult's law, and then osmotic pressure related to osmosis, which is the diffusion of water. So freezing point depression. So depression in this case means it goes down. So freezing points, which keep in mind are the same thing as melting points, just opposite direction on the phase change. But freezing points go down as you add solute. And again, the more solutes you add, the more they go down. In fact, this is why they salt the roads in cold country. Now, I live in Phoenix, Arizona, and oddly enough, just yesterday, we got snow in different parts of the Phoenix area for the first time in over a decade. So at least in some of the outskirts that are at higher elevations, they sometimes occasionally get a little snow, but most of the time we don't get snow for a decade or two. Well, we just got some yesterday for the first time ever, and quite a bit. And we don't salt our roads because all that snow is largely melted at this point. But for some of you that might be from, say, Chicago or Minneapolis or something like this, you'll find that they salt the roads in the winter. And the salt they use is not sodium chloride. They actually use calcium chloride. So let's get that out there. Calcium chloride, which has a Van Hoff factor of 3. You get 1 calcium ion and 2 chloride ions. So with that Van Hoff factor of 3, it makes it have a larger impact. But that salting of the roads lowers the freezing point of water. And so normally, you've got a freezing point for water of 0 degrees Celsius. So we'll put a temperature scale on here. And so if you're at a temperature of, say, -5 degrees Celsius, so on a cold day in Chicago in the winter, all of a sudden then the water on the streets is going to be frozen solid and it's going to be ice. However, if you put a bunch of calcium chloride on the roads, all of a sudden now it dissolves in the water and stuff like this. And all of a sudden now, let's say the freezing point of water is like -10 degrees Celsius. And so all of a sudden now your freezing point, the point at which water freezes, has been depressed down to -10 degrees Celsius because you've salted the road. You've added a bunch of calcium chloride on there. And so now on a cold day where it's, you're at a point where it's -5 degrees Celsius outside, well, now that water on the roads is not going to be frozen because you're above this depressed freezing point. And as a result, that water is going to be liquid, which isn't as dangerous on the streets. It's, not as slippery when the streets are wet as when they're frozen. And so that's kind of the idea, is it depresses the freezing point, which means it's more likely that water is going to exist in the liquid form than in the solid form than under normal conditions. So a lot of people think, well, salt melts the ice. Well, sort of. But what it's really doing is it's depressing or lowering the freezing point of water. That's what's actually going on. And so if you see what's going on here, so if you kind of look at, let's say, some regular repeating crystalline structure that we're going to call ice. So crystalline ice, we're going to have each of those boxes representing a molecule of water here, and it forms in a nice, regular, repeating crystalline pattern. And so in the liquid phase, the molecules are moving around to some degree and stuff like this, and as you cool it down, those molecules slow down a little bit. They're not moving as fast, and at some key temperature, 0 degrees Celsius normally, the molecules are now moving slow enough that they can't overcome the intermolecular forces, largely hydrogen bonding, that's holding the molecules together, and it freezes into a nice crystal structure. Well, all of a sudden, if you take out one of these water molecules and you put in something of a different shape, let's say, different shape and different intermolecular forces, all of a sudden it puts a wrinkle into the crystalline structure of ice. And this doesn't fit the way a water molecule would. And as a result, we now actually have to cool those water molecules down slower than even normal. a lower temperature than normal to get them to freeze into a crystal with this imperfection there, this impurity there. And so that's what's behind kind of freezing point depression. And again, it doesn't largely matter what this guy's identity is, this solute. It just matters that he's not a water molecule and he doesn't fit the crystal the way another water molecule would. And that's why that freezing point's going to go down. And again, the more of these you stick in there, the more the freezing point is going to get depressed. Cool, so that's freezing point depression. So you've also got boiling point elevation. So freezing points go down, but oddly enough, boiling points go up. So, and we largely don't expect you to memorize freezing points or boiling points, except for water. Water's is probably one just worth knowing. So the freezing point of water, again, is 0 degrees Celsius, but the boiling point of water is 100 degrees Celsius. And whereas the freezing point went down here, we find out that boiling points actually go up as you add solute. So, and the reason for this is a little bit complicated and beyond the scope of what you're going to need to know for this class. But it turns out, sometimes you'll hear some people lie to students a little bit and say, well, the intermolecular forces get stronger when you add a solute. They might not. It's not necessarily about intermolecular forces. It turns out it's about something we call entropy, which is a term involving a chapter on what's called thermodynamics, which is not something you're going to likely see in a high school chemistry class. And it's a little bit complicated. So that's why we're not going to cover it. So just suffice it to say there is a reason. It is complicated. So, but boiling points go up, and it's not about intermolecular forces. So freezing points go down as you add solute, boiling points go up as you add solute. So, and then finally you get vapor pressure depression. And it turns out so that if you had a glass of water, as you add more solute into it, so you'd actually end up with less vapor, water vapor, above that glass. And the more solute you add, the less water vapor you end up with there. So like if I told you, we have a humid day, it's humid outside, that means there's a lot of water vapor in the air. So, well, it turns out as you add solute into water, you end up with less water vapor, less humidity, if you want to call it that. So, and I realize humidity is related to temperature and stuff and other complex phenomena too. So, but how much solute is in the water also affects how humid, really how much water vapor there is. And we call that measure of that water vapor the vapor pressure. And so adding a solute causes the vapor pressure, in this case of the water, whatever the solvent would be, to go down. It's a depression. And it's governed by what we call Raoult's law, which is a mathematical expression we'll see in a little bit. So, and finally, osmotic pressure, related to osmosis, the diffusion of water. We will deal with that kind of separate from the rest of these, all at the end. All right, so before we look at the math involved in this, now that you understand that freezing points go down, boiling points go up, and vapor pressures go down, so there's some questions we could ask that don't require you to actually do a calculation. So here we've got the same compounds we studied before, we looked at the Van Hoff factors, and I'm going to give you equal concentrations of all four. And then I'm going to ask you a couple different questions. I'm going to say, which one has the highest boiling point? Well, again, boiling points go up as you add solute. Well, these are all equal concentrations, and even though they're all initially equal concentrations, they don't break up into an equal number of pieces. We saw that NaCl breaks up into 2 pieces. So methanol doesn't break up into any additional pieces. Barium hydroxide breaks up into 3 pieces, and aluminum nitrate breaks up into 4 pieces. And so even though initially it looks like we have equal concentrations, if you factor in how many pieces they break up into, you can get a total solute concentration. And so for NaCl, that total solute concentration would be 2 molal. For the methanol, it would still simply be 1 molal with a Van Hoff factor of 1. For the barium hydroxide, so it would be 3 molal total concentration of ions, of particles, of pieces. And then for aluminum nitrate, with a Van Hoff factor of 4, 4 times the 1 molal would be a 4 molal concentration. And so the aluminum nitrate is going to have the greatest concentration of particles. And therefore, it's going to affect these colligative properties the most. And therefore, it's going to have a boiling point that has gone up the most. It'll have the highest boiling point. It'll have the freezing point that has gone down the most. It'll have the lowest freezing point. And then it'll have a vapor pressure that has also gone down the most. It would have the lowest vapor pressure of water above that solution. And so in this case, what they're really testing you on then, with all equal concentration of solutes, is just to see if you know your Van Hoff factors. The one with the largest Van Hoff factor, therefore breaks up in the most pieces, has the highest boiling point, the lowest freezing point, and the lowest vapor pressure. That's how that works. Now, if they want to make this a little harder, they can, and that's what we're going to do in this next one. And I'm going to give you all different concentrations in this next example. So if I give you all different concentrations, it is not such an easy comparison. And a lot of students look at this and they're like, he's the highest concentration, he affects things the most. Well, again, it also, you got to factor in the number of pieces. So like with 2 molal NaCl, and I haven't mentioned it yet because we haven't seen the math, but molality is going to be most convenient when looking at freezing point depression and boiling point elevation. But with 2 molal NaCl, because it breaks up into 2 pieces, you end up with 2 molal sodium and 2 molal chloride for a total of 4 molal concentration of ions total, 4 molal concentration of particles. And so what you really got to do here is take the Van Hoff factor times the molality. And so in the case of NaCl, we've got a Van Hoff factor of 2, the molality is 2 molal to get us 4 molal. If we do the same thing for the methanol, well, again, methanol's just got a Van Hoff factor of 1, so its molality is still going to be its molality. It's just 1.5 molal. For the barium hydroxide, it breaks up into 3 pieces. So in this case, the I times the M would be 3 times the 1.2, 3.6 molal. And then finally for the aluminum nitrate with a Van Hoff factor of 4 and 4 times 0.9, also 3.6 molal. Cool, so if all of a sudden now we look at this and we say, okay, which one's gonna have the highest boiling point? And now we realize, oh, it was the NaCl, but not for the reason we thought. So because its total concentration of all dissolved species is the highest. Not its initial concentration, but the concentration of all dissolved species once you factor in that Van Hoff factor. And so in this case, that NaCl has the highest boiling point, it's gone up the most. It has the lowest freezing point, the one that's gone down the most, and the lowest vapor pressure. So could ask this in a little bit tricky way. So oftentimes they'll ask this in such a way that the one that had the highest overall concentration of the entire solute is not the right answer, unlike what I did here. So, but one other thing they might do to you here is trip you up on the freezing point. And they might ask you which of these solutions not has the lowest freezing point, not the one that's gone down the most, but which one has the highest freezing point, which is which one has gone down the least. So again, if you look at our freezing point here, normal freezing point again of water is 0 degrees Celsius. So, and all of these solutions, I guess I should have maybe represented it like this. All these solutions are going to have a freezing point lower than 0. The one that has gone down the most, though, was the NaCl. So it turns out the barium hydroxide and the aluminum nitrate should have gone down equal amounts since they have equal total concentration of ions. So we got the barium hydroxide and the aluminum nitrate here. So, but then it's the methanol, which has the lowest concentration of total dissolved species, that goes down the least amount. And so if you look, let's try that again. CH3OH. So because he's the one that's gone down the least, he ends up with the highest overall freezing point. So again, if I said which one's got the lowest freezing point, again, the one with the greatest total concentration of ions, NaCl. If I said which one's got the highest boiling point, the one that's gone up the most, again, it's the NaCl. But if instead of asking you for the lowest freezing point, get tricky and ask you for the highest freezing point, well, then I want which one has gone down by the least amount, the one with the lowest total concentration of dissolved species. That's how that works. Cool. So we haven't actually done much for math yet, but let's take a look at the math involved with each of these. All right, so we're going to start with freezing point depression here, and here's the lovely equation I've given you. The change in the freezing temperature, so is negative I, the Van Hoff factor, times this lovely Kf, the freezing point constant. And for water, I put it in a table on your handout. For water, it's 1.86 degrees Celsius per molal concentration. So, but every liquid has its own unique Kf value here. So freezing point constant, and then times the molality. Now, one quick thing to note, if you are using a textbook in addition to my lessons here, so almost without fail, this equation is actually reported to look like this. There's no negative sign out front. And so when you calculate it, this delta T, you're supposed to know that for freezing points, they go down in temperature. So whereas the truth is, if we put the negative sign out front like I've done here, well, then a negative change means it went down, whereas a positive change means it went up. So, but they just expect you to know that freezing points go down. So again, most textbooks and technically the general equation doesn't have the negative sign there. So, but I put it in my study guide like so, just so we know, no ifs, ands, or buts, it goes down for freezing points. So, but this is our mathematical equation here for how we calculate how much it changes by. So in this case, if we, first question on your handout there in this section is, what is the freezing point of a 1 molal solution of NaCl in water? So in this case, we'll just plug and chug. So in fact, let's do this in a different color. Keep that regular equation separate. So in this case, we've got delta TF equals negative I, and again, the Van Hoff factor for NaCl is 2, times the freezing point constant of 1 point, let's make that prettier, 86 degrees Celsius per molal, and times a molal again of 1 molal in this case. So if you notice, we've got I times M as part of the equation. And again, the whole point of that is that you've got the molality of the original solute, but you have to multiply it by how many pieces it dissociates into to get that total concentration. So, and then you multiply it by this freezing point constant. If you look at what this freezing point constant actually says, it says that water's freezing point changes 1.86 degrees Celsius per every molal concentration of ions. And so if you have 2 molal, then you double this number. If you have 5 molal, then you multiply this number by 5. So that's what that number actually means. And so in our case, we've got 1 molal NaCl, but because it dissociates into 2 pieces, that actually leads to a 2 molal overall concentration, which is why in the end, you're going to multiply 1.86 here by 2. All right, so if we work this out, 1.86 times 2, we'll use the trusty calculator and get 3.72 degrees, and specifically in our case, the negative 3.72 degrees Celsius. Cool. Now in the case of water, what's nice is that if you want the freezing point, well, the freezing point of water here, normally what you'd do is you'd have the original, and I'll just call it the initial freezing point, plus the change in the freezing point to get the new freezing point. Well, in our case, what's nice though is that water's original freezing point is 0 degrees Celsius. And so the change in the freezing point is the new freezing point. So the new freezing point for water is simply negative 3.72 degrees Celsius. Now, had this been any other liquid whose freezing point was any other number but 0, well, then if I asked you for the freezing point itself, you take the change that you calculate from the equation and add it to that original freezing point to get the new depressed freezing point. That's kind of how that works. All right, it turns out that boiling point elevation is almost directly analogous here. So for boiling point elevation, we have the change in the boiling point temperature is equal to the Van Hoff factor. Now there's a boiling point constant, and these boiling point constants, they're different than the freezing point constants. And again, every liquid has its own characteristic boiling point constant. You can look them up in tables online or in the back of your textbook kind of a thing. And then again, times the molality. So almost a directly analogous equation, except notice there's no negative sign in front of this one because the change should be a positive change. Boiling points do indeed go up. All right, turns out we're going to find the boiling point once again for 1 molal NaCl, but the boiling point constant given on your handout there is 0.51 degrees Celsius per molal. So again, that means that the boiling point goes up about half a degree for every molal concentration of dissolved species. So in this case, we'll calculate out change in your boiling point equals I, again, 2 for NaCl, Kb, 0.51 degrees Celsius per molal, and our molality, again, is still 1 molal for our NaCl solution we're dealing with here. And 2 times 1 is 2, and 2 times 0.51 is about a 1 degree change. In this case, 1.02 degrees Celsius. Now, if I asked you not for the change in the boiling point, how much it went up by, it went up 1 degree roughly, but if I said, what is the boiling point? Well, then you take the normal boiling point, the original boiling point for water, 100 degrees Celsius, and add that change of 1.02 degrees in, and you'd get 101.02 degrees Celsius. So be careful on the question. So here we're not adding it to 0. It's not the original boiling point but, for water. So in this case, you could be asked, what is the change in the boiling point, or just what is the boiling point? Either one of those is fairly common. So you should be prepared to either just to calculate the change directly, or to calculate it and then add it to the original boiling point of your substance, in this case, water. Nice round number. And again, for water, you are probably expected to know that water's freezing point is 0 degrees Celsius and water's boiling point is 100 degrees Celsius. But for any other substance, they're going to have to tell you. Now on your handout in your table, along with the freezing point constants and boiling point constants, I also listed the freezing point and boiling point of water, the normal ones. So, but again, for any other substance, they're gonna have to provide you with those as well. All right, so let's take a look at vapor pressure depression next. And vapor pressure depression is governed by what's known as Raoult's law. So if you look on your study guide there, Raoult's law is given as partial pressure of whatever you're talking about equals mole fraction. So we're not using molalities anymore, we're using mole fractions. So, and then times the partial pressure of that substance, and then they give an asterisk. And that asterisk means pure. So if you've got an aqueous solution and you want to know what's the vapor pressure of water above that solution, well, you need to figure out what's the mole fraction of water, and then you need to know what pure water's vapor pressure would be. That's kind of how it relates that. And so this equation is the one we're going to use. So, but if you look at what it actually means, it'd be a little bit different. So the problem we're going to do here, so we're going to have an aqueous solution. So it's in water. And in our question, we've got what is the vapor pressure of water at 25 degrees Celsius above a solution containing 162 grams of water and 32 grams of methanol. So that's what we're actually doing here. And again, this is going to be related through the mole fraction. In this case, the mole fraction of the water. And so to figure out the mole fraction, we have to convert both of these into moles. But before we can even touch this, we have to know, well, what is the vapor pressure of pure water? So, and again, there's a table on your study guide given there. So it gives you some constants for water, and it gives you the vapor pressure of water at 25 degrees Celsius of 24 torr. So if we had another beaker over here, so, and this beaker has pure water, it means that the pressure of water vapor up here, the water molecules that are up here, would be 24 torr. Now in this case, because this is not pure water over here, then the partial pressure or vapor pressure of water molecules up here, we should expect it to be less, because vapor pressures are depressed as you add solute. And the more solute you add, the more they get depressed. Vapor pressures go down. And so in this case, we're going to expect it to be lower than 24 torr by some amount. So cool. So what we want to do is convert both of these into moles. And in this case, 162 grams of water. So 1 mole of water weighs 18 grams. And I've set this up so nicely that this equals exactly 9 moles of water. And it turns out if you look at methanol here, carbon is 12, oxygen 16, and then 4 hydrogens that are 1 each, gets you to exactly 32 grams. And so it turns out I gave you exactly 1 mole of the methanol here. And so I made the math nice, because again, if you learn this stuff with nice numbers, it's way easier to learn. So, but you should be prepared for a little more complex numbers on some of the practice you do. But in this case, we got 9 moles of water, 1 mole of methanol. And that's, again, this calls for not the mole fraction of the solute, but the mole fraction of the solvent, and water in this case. And again, that's 9 moles of water out of a total of 10 moles of everything, 9 plus 1. That's our mole fraction. And again, the vapor pressure of pure water at this temperature is 24 torr. And so now we can calculate what the vapor pressure is above this solution. And since this solution in terms of moles is only 9/10 water, you only end up with 9/10 of the vapor pressure as well. And so if you work at this, 9/10 or 0.9 times 24. So 10% of 24 is 2.4. So we'll subtract that off as one way to do it. So, and that's going to get us 21.6 torr. So, and again, just use your calculator. I'm just doing the math in my head here, but if we do 0.9 or 9/10 times 24, you indeed get that 21.6 torr. And so our vapor pressure went down 2.4 torr from the normal value. Cool, so we've covered freezing point depression, boiling point elevation, and now Raoult's law, which governs vapor pressure depression. Let's take a look at osmotic pressure. All right, so the last one we got to talk about here is osmotic pressure, and there's a lovely equation regarding it here. So here, the Greek letter pi represents osmotic pressure. We can't use the letter P because P usually refers to gas pressure. So we use the Greek letter pi for osmotic pressure, and it's related to the molarity, the universal gas constant does show up there, and then the temperature in Kelvin. Cool, so what is osmotic pressure? Well, we got to talk about what is osmosis, and to talk about osmosis, we probably should talk about diffusion first. So let's say I took a lovely little glass bottle of cologne, and I took the cap off, and I put it in the corner of the room. So eventually you'd be able to smell that cologne throughout the entire room. So that cologne would spread out throughout the room, at least some of the cologne vapors, and eventually you'd be able to smell it anywhere in this small little room. And even in larger rooms, you'd probably still at some point be able to smell it. So that is diffusion. And diffusion, simply put, is when a substance travels from areas of high concentration in the bottle out to areas of lower concentration. That's diffusion. Well, osmosis is the diffusion of water. It's where water goes from areas where it's high in concentration, where it's most pure, out to areas where it's lower in concentration, where the water's less pure. And so we can look at it in terms of water's concentration. Osmosis is the diffusion of water from areas where water is in a high concentration to areas where water is in a lower concentration. So, but instead of looking at water concentration, we often look at it usually in terms of solute concentrations instead. And so if we're going from areas where water is in a high concentration, well, then our solutes must be present in a lower concentration. And if it's moving to where water is in a lower concentration, well, then it must be moving to areas where the solute is present in a higher concentration. And so if you define osmosis in terms of solute concentrations instead of water concentrations, it's the exact opposite. And you could say that osmosis is the diffusion of water from areas of low solute concentration to areas of high solute concentration. So just want to make sure you'd seen it both ways. I usually like to just talk about it in terms of water concentration, but because you are likely to see it in other courses in terms of solute concentration, I wanted to present it both ways there. All right, so in our case here, we're going to have this lovely two-chambered thing, or it's really a single chamber separated by what we call a semi-permeable membrane. And that semi-permeable membrane here that I'm representing by a dashed line, it is permeable to water and not to any solutes. So water can cross back and forth, solutes cannot. And so on one side of this semi-permeable membrane, we've got pure water, but on the other side, we've got a 1 molar solution of NaCl. So it's mostly water, but it does have some sodium chloride in there as well. And so as a result, water is going to want to travel from one side to another. And if we look at water traveling from a high concentration of water to a lower concentration of water, we could see that the water is going to want to travel from high concentration where it's pure to lower concentration where it's less pure. If you looked at it in terms of solute concentration, the water is going to want to travel from where there's a low solute concentration to where there's a higher solute concentration. Same way, you get the same direction. But the water wants to cross this membrane. Now you could say that the NaCl wants to cross the membrane and diffuse across as well. But again, we've got a selectively permeable membrane that only is permeable to water. NaCl is not allowed to cross. And so as a result, the water wants to travel from the right-hand side to the left-hand side, and that's going to want to cause this lovely chamber to rise in volume and this one over here to fall in volume. So, and governing that, I've got a couple of pistons here. So, and the water wanting to rise over on this side is going to put a pressure pushing up on this piston. And the amount of pressure I have to push down with on this piston to keep that from happening, to keep that water from rising, so the exact amount would equal what's called the osmotic pressure. So, which we can calculate with this lovely equation. So that's what's going on here. And in this case, this molarity that you're plugging in here is the difference in molarity between your two solutions. Well, if one of them's got a 0 molarity and one of them's got a 1 molarity, well, then it's going to be 1 molar. Now, I'll warn you here, most of the time you'll see this equation presented just like I've written it here. However, the one I gave you on your handout also includes the Van Hoff factor because you do have to factor that in. So for whatever reason, they decided whenever they made this equation, well, don't put the Van Hoff factor in. We'll just make sure students realize that they do need to factor it in even though we didn't put it in the equation. Well, I'll put it in mine. So you do need to factor in if something is an electrolyte and breaks up into multiple ions, like NaCl, which has a Van Hoff factor of 2. And so in this case, if we calculate out our osmotic pressure, it's going to be 2 times our 1 molar concentration difference So our gas constant, 0.08206 liter atmospheres per mole Kelvin. So same gas constant we saw with the ideal gas law, PV equals nRT, same exact one. So typically is going to be provided for you. And then finally our temperature, and they got to tell us what temperature this is at. In this case, 25 degrees Celsius, which is 298 Kelvin. Cool, and from there it's going to be some plugging and chugging. And so we've got 2 times 1 times 0.08206 times 298. And we're going to get 48.9 atmospheres. Cool, so that's a pretty significant osmotic pressure here. And so got a couple questions for you. If you were here in person, my first question would be, so what if I applied a pressure on this piston of 30 atmospheres? What would happen? Well, again, the water itself, and wanting to cross this membrane due to osmosis, is applying a pressure of 48.9 atmospheres. So if I'm only pressing down on this piston with a pressure of 30 atmospheres, well then osmosis is going to win and the water level is going to rise. Then my next question for you is, well, what if I pushed down on this piston with a pressure of exactly 48.9 atmospheres? Well, then nothing's going to happen. The water's not going to rise, but it's not going to fall either. So, but the more interesting question though is, what if I push down on this piston with a pressure of 100 atmospheres? Well, if I push down on this piston with a pressure of 100 atmospheres, well, then it's going to go down, opposite of the way osmosis is pushing. And that's going to force more water to the other side, which means we're going to make more pure water because the NaCl can't cross. And so what we're doing is we're doing something that is the reverse of osmosis that leads to more purified water. That's how your reverse osmosis, or RO system, if you have one, works. You're just applying a pressure so that is greater than the pressure being applied by osmosis to force water the opposite direction and make more purified water. Now, if you look at what happens though, is that if you start forcing more and more water over here and making more purified water, what's going to happen to the concentration of NaCl over here on the left-hand side as we force more of the water out of this side? Well, that concentration of NaCl is going to go up. And if the concentration or molarity of NaCl goes up, well, then so does the osmotic pressure. And so as you force more and more water to the other side in your RO system, so you might still be pressing with 100 atmosphere pressure, let's say, but the osmosis is no longer going to be pushing back with 48.9. That's going to rise. And eventually, if you force enough water over here, that concentration of NaCl is going to go high enough, somewhere a little over 2 molar is going to be the case, where it actually has an osmosis of 100 atmospheres. And at that point, if the hardest your RO system can push is with 100 atmospheres, well, then you're done. You can't make any more purified water. And what your RO system does at that point, it ejects all the contents from this side of the container down the drain, and you get to start over again. Cool, so that's how your RO system works. Just want to make sure you're aware of that. Cool, this is colligative properties in a nutshell. Again, freezing point depression, boiling point elevation, vapor pressure depression, osmotic pressure. You should understand them qualitatively and quantitatively. And again, you should know how that Van Hoff factor factors in. Now, we did do a calculation with osmotic pressure here at the end, but I will warn you, this is probably the least likely of the calculations you're going to see. It is part of the standard curriculum. It is something you could encounter. I'm just letting you know it's probably the least likely one. Now, if you found this lesson helpful, would you consider giving me a like and a share? Again, that's the best way you can ensure that other students are going to see this lesson. If you're looking for the study guide that goes with this lesson, if you're looking for practice quizzes, things of the sort, check out my premium course on chadsprep.com. A free trial is indeed available.